This is an overview video on how to set up a simplified tensile load case in a two-force member, such as a connecting rod and an internal combustion engine. So we're going to use Ansys Mechanical 2021 R2 here, and we are going to activate the static structural solver here in the workbench. And we have a CAD file already prepared, so we can skip the geometry creation and we can go directly to model here. I encourage you to look at the other videos here that we have uploaded for tutorials regarding all the different analysis systems and then some of the workflow that's showing up here in, I guess, this checkbox list when we select static structural. So we'll wait for that engine here to load, and then we'll go ahead and import our CAD into the workspace here. You can see it's already propagated the static structural analysis type, so we'll go import, browse to a geometry file, and we want this step file here, which is an internal combustion engine connecting rod. You'll see that it imports here into two pieces, so there's the rod itself and then the end cap. This is held together with fasteners. You'll see that in a moment here when I zoom out. So this is kind of the vertical orientation of the rod. So there is a big end at the bottom that attaches to the crankshaft, and then the small end here that attaches to the wrist pin or the piston. So the darker blue is the connecting rod itself, this one here, and then the end cap is this. Typically it's held together with fasteners, and those bolt forces are preloaded with some applied torque, obviously, to keep these two pieces in contact with one another under the forces of the rotation of the engine and the combustion pressures and all of those other dynamic things. So we're going to ignore the fact that there is fasteners here. Obviously that would be a much different analysis, and this is just a simplified analysis to look at optimizing the kind of the member itself, the section in the middle of the member for a tensile load case. So this is a steel connecting rod, so the part material assignment is just structural steel. Traditionally, that's what connecting rods are made out of. I think in reality, this is a 4340 alloy steel of this particular connecting rod. The next thing is, because we are going to ignore the actual bolts that are holding these two pieces together, we're going to leverage the automatic contact detection here in the connections. So the two contact regions are that are automatically detected are these two, the blue and red surfaces that are these end cap surfaces. So we are just forcing these to be bonded together, so it's as if it was just all one piece. And this will have a large effect here. Obviously, if you're investigating the fastener failure, that would this is a totally meaningless or nonsensical assumption. But if we're just looking at optimizing the beam geometry here of this I-beam in the middle of the component, this is a fairly reasonable assumption, as the stress distribution in the middle is not going to be affected by any of those bolt pretension forces there. So we'll go ahead and generate a mesh here. So we'll right click and click generate mesh, and you'll see that it'll automatically start generating a mesh for all of the small surfaces here and defeature some of them, because I think this CAD geometry is quite complex. So you see what we end up here with, a nice symmetric tetrahedral mesh. This would be a good opportunity to invoke symmetry here, at least along one plane, but even two. But we'll just show, for the purposes of this analysis, it's a fairly small model. We'll show the entire component here so you get an idea of what's going on without having to wrap your brain around the symmetry constraints. To save some run time, and if you added complexity to the model, that'd be a great place to start. So we'll go to static structural here, and we'll start applying our boundary conditions. So the load that we want to apply is going to be at the pin end here. So we'll click loads, and we'll actually apply a load, so a force, and we're going to apply 1,000 newtons just arbitrarily. That's kind of a very let's say non-severe loading event for this particular engine. And we're going to select these surfaces here. So these bearing surfaces at the pin end, and we're going to be pulling upwards here. So we'll actually select the magnitude and the direction here. We will, instead of a vector, we'll define it by the components. So we'll say 1,000 in the x direction here, and that's positive, meaning up. So we're going to pull with 1,000 up, as if the piston assembly is tearing the connecting rod apart in tension. So there's two ways an internal combustion engine predominantly, or at least the connecting rod. There's some lateral forces on the piston, but the connecting rod is a two-force member ideally, if we're ignoring the friction at the bearings and the fact that there's really no bending in the idealistic case. So as the piston comes to the top dead center and reverses direction, all of that inertial force is trying to tear away the connecting rod from the crankshaft in tension. What we would like to simulate is that. We could also simulate compression potentially if we were pushing downwards due to the combustion pressures from the combustion event. So that's another alternative. And we can look at potentially other events, but for or load cases, for the purposes of this demonstration, we'll look at tension. So we're going to apply 1,000 newtons upward on those two faces, and we will ensure that those are selected. We'll zoom in here. 1, 2, control click to select multiple faces and click apply. And now we have 1,000 newtons of force applied in that direction. We can apply a surface effect or a direct force application. So the surface effect will give a slightly different ovalization here. We'll see that in the deformed shape when we exaggerate the deformation. But now we have our force applied at the pin end. The other end, we want to apply a cylindrical constraint. That'll allow us to visualize some of the stresses in compression on that end as you're pulling up. So we will do a support and go to cylindrical support, and we will do these two surfaces, three surfaces, apologies, that one's split there. We'll click apply, and we want it to be fixed in the radial, axial, and tangential directions. And now we pretty much have everything ready to go to solve this. So we'll go ahead and click solve. It should take 30 or 40 seconds to solve here. So you can see it building the mathematical model and going through the analysis engine steps here. So we'll just let that run in the background. And now we will investigate our deformed shape and some of the stress values and even some principal stresses, some different quantities of stresses. So we'll click on solution. We'll enable the total deformation plot, the directional deformation plot, von Mises equivalent stress, and our vector principal stress, and we will right click here and click evaluate all results. And you'll see that now we have our deformed shape here in tension. So you can, this is deformation here, but we'll go to equivalent stress. So our von Mises equivalent stress is right there. And you can see, obviously now we have some ovalizing here of the pin end. We are exaggerating the scale. This is the actual deformation scale, so not very visible. So we'll go to the automatic scale here, and you can see how this is deforming and how the stress is flowing in the beam part of the connecting rod. So we'll click pause here, and kind of in this sharp radii here, in the transition between the I-beam profile and this pin end, is where we're getting our maximum stress of around 67 megapascals, which is kind of what you'd expect. But you can see that even progression here. So it's a fairly optimized beam profile, not amazing, but fairly optimized, and you can see how it grows here towards the pin end. We can even see the vector principal stresses to see different direction and forces here on each of the elements and where the stress direction is. So you can see that here and how the force is flowing in the beam section of the connecting rod. As I mentioned, the total deformation under this amount of load is 3.14 e to the negative 6 meters. So we can convert that. So 3.14 divided by 1. So that is around 0.003 millimeters of elongation. So quite small, obviously, which is what you'd expect for this kind of moderate load. This obviously gives a very simplistic overview of how to analyze this two-force member. We're ignoring, first of all, a lot of the inertial effects we're distilling down into a static load case. So all of the various inertial loading and static loading and combustion loading we're kind of doing in a quasi-static nature here. So the engine itself, we're extracting a load case and applying it as a static event or a static structural simulation here. So there, we can do another tutorial video on just extracting the load case from a particular event in the combustion cycle or the four-stroke cycle of the engine, but we'll save that for another video. So hopefully that was informative and gives you an idea on how to approach this simplistic simulation and do some kind of rudimentary optimization afterwards. Thank you.